Corrosion testing, advanced methods to assess material durability and safety. Corrosion testing overview, definition of corrosion, why corrosion testing matters. Corrosion testing is a critical engineering discipline focused on evaluating how materials, particularly metals and alloys, degrade when exposed to environmental conditions over time. The primary purpose of corrosion testing is to understand material behavior in service environments and to ensure structural integrity, safety, and reliability across an asset's intended lifespan. In engineering practice, corrosion testing supports informed material selection, appropriate protective measures, and compliance with regulatory and industry standards. Engineers rely on corrosion test data to predict service life, prevent catastrophic failures, and minimize unplanned downtime. The process typically involves controlled laboratory testing, accelerated exposure methods, and field evaluations that simulate real-world environments such as marine, industrial, or atmospheric conditions. By systematically studying corrosion mechanisms, engineers can identify vulnerabilities in design, improve maintenance strategies, and reduce lifecycle costs. Corrosion testing also plays a major role in quality assurance, helping verify that materials and coatings meet specification requirements before deployment. Across industries such as oil and gas, aerospace, construction, and manufacturing, corrosion testing forms a foundation for risk-based decision-making and sustainable engineering design. Corrosion is defined as the gradual degradation of a material, usually a metal, due to chemical or electrochemical reactions with its surrounding environment. From an engineering perspective, corrosion is not merely surface damage but a complex process involving electron transfer, material dissolution, and environmental interactions. Common forms of corrosion include uniform corrosion, pitting, crevice corrosion, galvanic corrosion, and stress corrosion cracking. Each form presents unique risks and requires different testing and mitigation strategies. Corrosion typically occurs when a metal is exposed to moisture, oxygen, salts, acids, or other reactive substances that drive electrochemical reactions. Understanding the definition and mechanisms of corrosion is essential for engineers, as it directly influences material selection, component design, and protective system implementation. A clear grasp of corrosion fundamentals allows engineers to anticipate failure modes, design against degradation, and apply appropriate testing methodologies to validate performance under expected service conditions. Corrosion testing matters because material degradation can have serious safety, financial, and environmental consequences if left unmanaged. In critical infrastructure and industrial systems, corrosion-related failures can lead to leaks, structural collapse, equipment malfunction, and hazardous releases. Corrosion testing provides engineers with quantitative data to assess risk, prioritize maintenance, and implement preventive measures before failures occur. From a cost perspective, proactive corrosion testing helps reduce repair expenses, extend asset life, and avoid costly shutdowns. It also supports regulatory compliance, as many industries are required to demonstrate material durability and corrosion resistance. By predicting service life and identifying degradation trends, corrosion testing enables better planning and asset management. Ultimately, corrosion testing is essential for ensuring public safety, protecting investments, and supporting sustainable engineering practices. Engineering principles and applications: corrosion mechanisms, environmental factors, and material selection. Understanding corrosion mechanisms is fundamental to interpreting corrosion test results and applying them effectively in engineering design. Corrosion mechanisms describe how and why materials degrade under specific environmental and mechanical conditions. Electrochemical corrosion involves anodic and cathodic reactions, while chemical corrosion may occur at high temperatures without the presence of an electrolyte. Factors such as material composition, microstructure, surface condition, and environmental variables all influence corrosion behavior. Engineers must understand these mechanisms to select appropriate test methods and interpret results accurately. By linking corrosion mechanisms to real-world service conditions, engineers can design components that are more resistant to degradation and failure. This knowledge also informs the development of protective coatings, inhibitors, and cathodic protection systems. Corrosion mechanism analysis bridges laboratory testing and field performance, making it a cornerstone of corrosion engineering. Environmental factors play a decisive role in determining corrosion rates and failure modes. Parameters such as temperature, humidity, pH, salinity, and pollutant concentration significantly influence corrosion behavior. For example, marine environments with high chloride content accelerate pitting and crevice corrosion, while industrial atmospheres may promote acidic corrosion due to sulfur compounds. Corrosion testing often involves simulating these environments to assess material performance under realistic conditions. Engineers must evaluate how fluctuating environmental conditions impact corrosion risk over time. Understanding these factors allows engineers to tailor testing protocols and select materials that can withstand specific exposures. Environmental awareness also supports the development of mitigation strategies, such as material upgrades or environmental control measures. Material selection is one of the most effective ways to manage corrosion risk, and corrosion testing provides the data needed to make informed decisions. Engineers compare corrosion resistance across candidate materials by exposing them to standardized or simulated service environments. Test results help identify trade-offs between cost, performance, and durability. Factors such as alloy composition, heat treatment, and surface finish all influence corrosion behavior. By integrating corrosion test data into material selection processes, engineers can avoid premature failures and optimize lifecycle performance. Proper material selection also reduces reliance on costly protective measures and simplifies maintenance planning. Corrosion testing thus supports a systematic, data-driven approach to engineering design. Testing methods and standards: laboratory testing, field testing, and industry standards. Laboratory corrosion testing provides controlled conditions for evaluating material performance and comparing alternatives. Common laboratory methods include salt spray testing, immersion testing, electrochemical testing, and cyclic corrosion tests. These methods allow engineers to accelerate corrosion processes and obtain results within practical timeframes. While laboratory tests may not perfectly replicate field conditions, they offer repeatability and standardization essential for quality control and material qualification. Engineers must understand the limitations of laboratory tests and interpret results in the context of real-world service environments. Properly designed laboratory testing programs provide valuable insights into corrosion resistance, coating performance, and degradation mechanisms. Field corrosion testing involves exposing materials or components to actual service environments over extended periods. This approach captures the combined effects of environmental variability, mechanical stress, and operational conditions. Field testing is particularly valuable for validating laboratory results and assessing long-term performance. Engineers use field data to refine corrosion models, adjust maintenance strategies, and confirm material suitability. Although field testing is time-consuming and less controlled, it provides the most realistic assessment of corrosion behavior. Integrating field and laboratory testing leads to more reliable engineering decisions. Industry standards play a crucial role in corrosion testing by defining accepted methods, procedures, and acceptance criteria. Standards organizations such as ASTM, ISO, and NACE provide guidance on test design, execution, and result interpretation. Compliance with standards ensures consistency, credibility, and regulatory acceptance of test data. Engineers rely on standardized tests to compare materials and demonstrate performance to stakeholders. Understanding applicable standards is essential for designing valid test programs and avoiding misinterpretation of results. Standards also support communication and alignment across multidisciplinary teams and organizations. Professional engineering practice: data interpretation, risk assessment, and lifecycle management. Interpreting corrosion test data requires technical expertise and engineering judgment. Test results may include weight loss measurements, corrosion rates, electrochemical parameters, and visual assessments. Engineers must evaluate data quality, repeatability, and relevance to service conditions. Misinterpretation can lead to inappropriate material choices or ineffective mitigation strategies. Effective data interpretation involves understanding test limitations, correlating results with corrosion mechanisms, and considering environmental variability. Clear data analysis supports evidence-based decisions and strengthens engineering recommendations. Corrosion testing supports risk assessment by providing quantitative inputs for evaluating failure likelihood and consequences. Engineers use corrosion data to prioritize assets, identify high-risk areas, and allocate maintenance resources efficiently. Risk-based approaches integrate corrosion rates, inspection data, and operational factors. This methodology improves safety and cost-effectiveness by focusing efforts where they are most needed. Corrosion testing thus underpins modern asset integrity management systems and informed engineering decision-making. Lifecycle management considers corrosion from design through decommissioning. Corrosion testing informs decisions at each stage, including material selection, protective system design, inspection planning, and end-of-life assessment. By integrating corrosion considerations early, engineers can reduce long-term costs and environmental impact. Life-cycle-focused corrosion management supports sustainability and responsible engineering practice. Testing data enables proactive maintenance and timely interventions, extending asset life and improving reliability. Advanced engineering considerations, coatings and protection, cathodic protection, and future trends. Protective coatings are widely used to mitigate corrosion, and corrosion testing evaluates their effectiveness under various conditions. Tests assess adhesion, permeability, durability, and resistance to environmental stressors. Engineers use test results to select coating systems appropriate for specific applications. Understanding coating performance helps prevent premature failure and reduces maintenance requirements. Corrosion testing also supports quality control during coating application and inspection. Effective coating strategies significantly enhance asset longevity and performance. Cathodic protection is an electrochemical technique used to control corrosion in pipelines, tanks, and marine structures. Corrosion testing supports the design and monitoring of cathodic protection systems by evaluating material response and environmental conditions. Engineers use test data to optimize system parameters and verify effectiveness. Properly designed cathodic protection reduces corrosion rates and extends asset life. Testing and monitoring are essential to ensure continued protection and avoid overprotection or system failure. Future trends in corrosion testing include advanced sensors, real-time monitoring, and data analytics. Emerging technologies enable continuous assessment of corrosion conditions and early detection of degradation. Engineers increasingly use predictive modeling and digital twins to enhance corrosion management. These innovations improve accuracy, reduce uncertainty, and support proactive maintenance strategies. Staying informed about technological advancements is essential for modern engineering professionals. Future-focused corrosion testing enhances resilience and sustainability across industries.